In this video, let's go ahead and try using our integrated rate laws. What do I mean by that? Well, remember in previous videos, we talked about the reason we came up with integrated rate laws was to allow us to predict the concentrations of our analytes at future moments in time. So let's do that. Here is an experiment represented by the data below, and we asked how much reactant remains after 95.5 seconds. And so we've got our time, our concentration, our national log of our concentration, and 1 over our concentration. And so we've already done this in a prior video, but what we noticed was that it's a first order reaction. And we know that because our blue graph here in the middle has an R squared of 1. So we know it is first order. And all first order reactions have this integrated rate law that is shown here. Natural log of A equals negative KT plus my natural log of my A at time 0. So what do we do with that? How do we plug in the 95.5 seconds? Or also importantly, how, if I'm given this here, can I remind myself of how to go from this to my integrated rate law and then plugging in my numbers? And so you first have to decide what's the point of the graph. The graph is to tell you the reaction order. Once you know that, you can know which integrated rate law to use, and then you can solve the question. So, natural log of A, remember that is my y. So we have y equals negative 0.0069x minus 2.3026. But we're going to solve this for just a general reaction. We want to solve this at a specific time. So what do I mean by that? What do I mean I want to solve this at a specific point in time? Well, my y is equal to my natural log of A. A is what I'm trying to solve. I'm trying to solve for the concentration of A at 95.5 seconds. That equals 0.0069. What was my x again? X stands for my t. So I need to plug in what point in time I'm trying to solve for. 95.5, and then that's an S for seconds. Minus 2.3026. Now notice something. What does the A0 mean again? It means time at A0. And so this is my time here at A0. And what is my natural log of A? Hey, it's 2.303, which was really close to my y-intercept, which is what I expected to see. And so when you're doing this, you can either use natural log of A0, this number here, or you can use the variable from your equation. Either one will get you approximately the exact same number. And so if we plug all this in, we end up with natural log of A equals negative 2.9615. Now how do I get rid of natural log? Remember, we raise both sides to the e, so we type into our calculator, second e button, raise to that answer. And I end up with the concentration of A equals 0.0517. And the units for that are molarity. Now, before you go further, ask yourself, does this answer make sense? What might I mean by that? Well, 95.5 seconds. Where do I expect that to be? I expect it to fall almost exactly right above here at 0.05. So I expect it to be just higher than 0.05, which it is. And so that is how you determine how much of a reactant remains after some period of time. You determine your reaction order, you determine your integrated rate law that you'll use, and then you use the trend line plus that information to solve for your final answer.